Oh, that was the last one. And now I'm listening. Listen. I'm not here for this situation. This is my home. Well, that's what I say. That's what I have to say. Oh, so this is more or less my home. That's common knowledge, right? For every class.
Okay, let's get going. I'm going to start with few announcements. One of them is that there's a homework due today. Hand in your homework over here. Pick up the solutions on your way out. There's also graded homework for you to pick up. The next homework, I'm going to announce it by the end of the... Did you get it already?
Not yet.
Okay. Shall I before I start the lecture, you want to give it to me, or are you going to give it to me at the end of the lecture? Okay. Okay. So I might announce it by the end of the lecture. If I don't, it'll be on the class website by 12 noon. It's just 6 problems out of Oppenheimer and Schaefer, so not a big deal. And the class website, I'll write it down on the board so that you can easily locate that. And the other announcement is that the second midterm, if you will, of the course is second quiz of the course, or exam of the course, whatever you want to call it. Test of the course is going to be on December 5th, which is the last day of Friday, December 5th, which is the last day of instruction. It'll either be in this room or Sibley. I'll make an announcement about that, and you can bring in 2 sheets and all that. That's about all the announcements let me put this on. That's about all the announcements I have. Anybody else? Anybody? Any questions? Yeah. You have this one, which is due. Today is the 14th, so this one is due on the 21st. It's due on the 21st. And let me also write down the web. www.inst.eec.berkeley.edu/EE123. That's what it would be. Then there's one that I assigned on the 21st, and it will be due. 28th is a Friday of Thanksgiving, but it would be due on December 1. Monday, December 1. So you'll just stop by Rosita Alvarez's office, hand it in on Monday, December 1 by 10 a.m. And I'm going to do my best, together with my grader, to have it returned to you by Wednesday, December 3rd. Okay? So there's this and one more, essentially. And, yeah. Don't know. You're asking. Yeah, I don't know that yet. Just sort of make things up as we go along. Each time I teach the course, I do things a little bit differently. So, any other questions or comments? Okay, let me get going. So, what we talked about last time was DFT, right? We talked about the fact that if you have an n-point sequence with n non-zero values, or a sequence of extent n, that's the best way of calling it. A sequence of extent n, it has a region of support that's of length n. Then you can either take this n-point DFT, or you can pad it with extra zeros and make an m-point sequence out of it and take an m-point DFT, where m can be any number, right? And so essentially, if you do an n-point DFT, you get n equally spaced samples of the DTFT of the sequence. If you do an m-point DFT of it, you get m equally spaced samples of the DFT of it, right? Both of those are. Thank you, Dan. Appreciate it. So both of those are possibilities. And then we also left last time's lecture by talking about this hypothetical or thought experiment, which was what happens if you have DTFT of any sequence. You don't even know whether that sequence was infinitely long, finitely long, or whatever. And you just sample it at n points, and you take inverse DFT of that, you get a new sequence. How is that new sequence related to the DTFT of the original sequence? And the answer was, is the original sequence periodicized with period n, which is how many samples you sample it at, and then just take one period. So those are the key things that we discovered last time. And we also talked about properties of DFT. And the purpose of this was to sort of remove some myths about the properties of DFT. In particular, you want to make sure that an inverse endpoint DFT of anything is always an endpoint sequence with region of support between 0 and n minus 1. It can't be outside that range. Furthermore, a forward DFT of any sequence, of any endpoint sequence, or an m-point DFT of any sequence, always results in an m-point DFT coefficients, where the indices of those coefficients are from 0 to m minus 1. It can be outside those range. So what I'm trying to say is that when you have if x of n has a DFT that corresponds to x of k, then if I multiply this by its exponential, I can't shift it because the region of support thing doesn't hold true. Instead, what you have to do is you invoke the relationship between DFT and DFS and find out that for this sequence, the inverse DFT is this. It's x of n minus n naught, which is what your intuition would have said, but you make it a periodic, and then you multiply it by r and n, which means take one period of it. The same thing is true. So pictorially, this is shown here. If this was x of n, this is x of n tilde, this is x of n minus n, n naught tilde, and then this is when you take one period of it. Pictorially, this is what happens. The same thing is true with other properties of DFT. If x of n and x of k are DFT and inverse DFT pairs, the DFT of x complex conjugate of n is not x complex conjugate of minus k, which is what your intuition would have told you. Rather, it's x complex conjugate of minus k, periodic, and then multiplied by Rn, which extracts just one period. Okay? And the same things hold true for symmetry properties. Again, x of e of k by itself has extent larger than n points. So you make it periodic, multiply by that. The same thing with the antisymmetric part of x. The same thing with the even part of e. The same thing with odd part of x. Okay, so these are the properties of DFT. Don't get tripped over them. For DFT and inverse DFT, if you give an n numbers, they give you n numbers. If the indices of the first n numbers are between 0 and n minus 1, the indices of the outcome is between 0 and n minus 1, and vice versa. The indices are always between 0 and n minus 1 if you're dealing with n-point things. Okay? They don't spill over to larger than n or negative values of 0 or values beyond 0. So that was a quick summary of last time's lecture. What I'm going to talk about today is just about the most important property of DFT, which is its use in convolution. And just to give you, excuse me, let me take my sweater out. It's a little bit hot in this room. But just to give you a little bit of a preview of what's going to happen, is that what we'll find is we'll continue with these properties. And in particular, I'm going to talk about convolution. So I'm going to ask you the following question. Okay, what happens if I multiplied x1 of k, endpoint DFT of x1, by x2 of k, endpoint DFT of sequence x2? What happens if I multiply that? Does it correspond to convolution? And what we'll find out, if I multiply x1 of k by x2 of k and then get x3 of k and take inverse DFT of x3 of k, would that correspond to convolution of those two sequences? And the answer is what? Periodic. It's periodic convolution. So does it correspond to linear convolution? No, and there's no chance in hell it could, because what? Because if I have an endpoint sequence x1 and another endpoint sequence x2, when I do the linear convolution, I get a 2n minus 1 point sequence. But this method I just talked about, multiply x1 of k by x2 of k. x1 of k is an endpoint sequence, multiply by x2 of k, another endpoint sequence, get x3 of k, another endpoint sequence. Take inverse DFT of x3 of k, I get an endpoint sequence. How could an endpoint sequence be linear convolution or convolution of two endpoint other sequences? It can't. So we absolutely have no chance multiplying these in the DFT domain does not really correspond to convolution. Convolution, as you know it in the sense of the beginning of the semester and last year, this is also called linear convolution. The normal convolution is called linear convolution. So if you want to do, and so we started off using DFT, bragging that it's useful for actual computations. It's the only thing. It's the only transform that can be used in practice and all those other things. But it's a shame if it can't be used for linear convolution, because linear convolution is the most primitive and most common signal processing operation that anybody does. And if you can't use DFT to do that, then essentially the whole semester was a waste. You might as well just go home and pack up. So, but don't despair. Don't pack up. We can do some modifications to these sequences in order to make DFT do linear convolution, and that's really what today's lecture is all about, is how can we get DFT to do good old linear convolution. And why do we care about convolution? Because it gives us the output of LTI systems, and those are the most important kind of systems we deal with. So let me just make a quick wrap up this announcement here. I found out the number of the homeworks that we're going to have due next Friday. It's 8.43, 8.44, 8.47, 8.50, 8.59, 8.60, and 8.63. Okay? There are 7 problems. You got it, and you're on your way to become a successful attorney here. Okay. So how do we use DFT to do convolution? That's the gist of today's lecture. Okay? So first of all, when I say convolution, I am implicitly meaning, or I'm in order to avoid confusion with we already talked about periodic convolution last time. The word convolution is the same as linear convolution. I just said it at the beginning of the lecture anyway. Okay. So when I say linear convolution, it's the same old convolution you learned many years ago. So x1, and when we use the symbol star, x1 convolved with x2 is equal to x3, and the definition of x3 of n in terms of x1 and x2 is the summation over k of x1 of k times x2 of n minus k. Okay? And convolution or linear convolutions are useful because they'll help us with LTI systems. In other words, if I have x1 or x of n going into an LTI system, and remember, LTI system is uniquely specified by its impulse response, h of n, and out comes y of n, which is summation over k of x of k, h of n minus k. Okay? So because convolution is used for LTI systems, we want to figure out how to use DFTs to do that. And so far, we've also talked about periodic convolution. And how did that work? Just to remind you from last time's lecture, it says if you have a periodic sequence x1 and you make a periodic convolution with another periodic sequence x2, and this is periodic with period n, and this is periodic with period n, you get a new periodic sequence, which is period with period n. And periodic convolution, I won't write down the equation for it, but just to give you a picture from last time, and if you can please put the camera on me, that's the thing where I said you put samples. Let's say I have a 5-point sequence because I have 5 fingers. I put these 5 points equally spaced along the cylinder, and then I click the cylinder at 2 pi over 5 angles, and when in this position I multiply this by that, 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 and get an answer. Then I click by 1, rotate by 1, multiply, add, rotate by 1, multiply, add, rotate by 1, multiply, add. That's how this periodic convolution thing worked, right? Everybody remembers that, okay? Well, now I'm going to talk about before I even talk about how to do DFTs for convolution, I'm going to talk about another thing, and that is circular convolution. And circular convolution deals with 2 finite length sequences. In other words, they don't have the sequences that you use for circular convolution don't have to be periodic, unlike periodic convolutions. So there are 2 finite length sequences, x1 and x2. This one is n-point long, and this one is n-point long. And the answer is also finite length, and it's also n-point. So x1 circularly convoluted with x2 gives me x3, and this one is also n-point long. And you notice that I'm using the same notation as periodic convolution. The reason is because there's a very close relationship between circular and convolution and periodic, and I could use an entirely different notation, but I don't, because I'm hoping that it's clear from the context. When you're convolving periodic sequences, this means periodic convolution. When you're convolving finite length aperiodic sequences, this is just a circular convolution. Okay, so this is circular convolution. I use the same symbol for it, and it gets 2 endpoint sequences and generates another endpoint sequence. And guess how it works? It makes this thing periodic with period n. It makes this thing periodic with period n. Then does a periodic convolution, gets the periodic answer, and then it extracts 1 period to get this. Okay, so it's a no-brainer almost. It's almost like periodic convolution. So how does here x let me call this x4 because I'm going to show something in just a second. But by definition, this is the definition of circular convolution. Is that x4 of n, which is the circular convolution of x1 and x2, x1 circularly convolved with x2, is just make x1 periodic, here it is, periodically convolve with x2 periodic, okay, get an answer, and then extract 1 period of it. That means multiply by r sub n of n. That's the definition. Here is, I put a little triangle here to show that that's formally, and a triangle here, the definition of circular convolution. Okay? And what I'm going to show now is that there's a relationship between the DFT of x4 and DFT of x1 and DFT of x2. Okay, so I'm interested in I'm going to show that endpoint DFT of x4 of n is equal to x1 of k times x2 of k. In other words, x4 of k, I'm going to show, is x1 of k times x2 of k, where each of these this is an endpoint DFT of x4, this is an endpoint DFT of x1, and this is an endpoint DFT of x2. And if it is indeed the case that multiplying products of two endpoint DFTs results in another endpoint DFT, then it doesn't seem like circular convolution is the same as, well, just take that back, okay? So how can we prove that? Well, from the properties of Fourier transform, we know, from the properties of discrete Fourier series, what we know is that when you periodically convolve two sequences, their DFSs get multiplied by each other. So we know from discrete Fourier series properties, and that's exactly why we even bothered about introducing discrete Fourier series, because its properties become very handy when you deal with DFT, sorry. We know from DFS properties that if I have two periodic sequences, x1 and x2, and I periodically convolve them, then what I get is, and I get a new sequence, let's call this x4 of n. That's also periodic. Then then we can show that x1 of k, which is DFS of x1 of n, and et cetera, et cetera, et cetera. Then I can show that x1 of k times x2 of k is equal to x4 of k. That's what we can show. And the proof of this is extremely straightforward. It's in the book, and it also follows exact same steps as you use to prove convolution in all the other senses, right? You plug it in, you take the DFS, and you apply formulas, and after like 5 lines of algebra, the answer just falls right out. So we know that already, okay? So if I apply a R function to this side, multiply a R function, that's the one that extracts one period, to both sides of this thing, what I end up getting is the following: R sub n of k times the left-hand side, which is x1 of k times x2 of k, is equal to R sub n of k times x4 of k. Well, what happens if I apply R sub n of k to this thing? Well, you get one period of that, and you get one period of that. So it becomes x1 of k times x2 of k is equal to x4 of k. So boom, we're done. So what that means is that, in words, it means that if I multiply endpoint DFT of two endpoint sequences, then you get the DFT of their circular convolution and not their linear convolution. Why? Because circular convolution is defined as making the things periodic, convolving them in a periodic way, and then extracting one period. So that's sort of what you end up with. And so what can we do to improve improve this sort of situation? And what does circular convolution really mean? How does it feel like? What's some example of circular convolutions? Well, let's do a pictorial example just to get a feel about how this thing works. So here's an example of a circular convolution. So suppose x1 of n is just delta of n minus n naught. And let me choose n naught equals 1. So that means x1 of n is just delta of n minus 1. Okay? So how does it look like? it's 1, 0, 0, 0, etc. And suppose x2 of n is an endpoint sequence. For example, okay, and suppose we make another endpoint sequence out of x1. So we make x1 of n, we pad it with enough zeros, so it's equal to 0 for n in between 1 and 0. It's equal to 1 for n equals 1, which is 1 here. And it goes all the way to n minus 1, so it's a whole bunch of zeros, and it's 0 all the way to between capital N and 1. Okay. Now let me grab Oppenheim and Schaefer and show some figures off of it, because it's a lot easier to use those pictures than have them drawn here. Let's look at figure 814. If you have it, open it up. Otherwise, I'll just put it under the camera. So here we go. Could you zoom in as much as you can, please? So how does a circular convolution of an endpoint? So this is our regular endpoint sequence. And here's, it's x2 of m. Can you focus it so that, okay, great, thank you. So this is an x2 of m. It has non-zero values at index 0, 1, 2, 3, 4, and that's it. And this is the delta function that we're talking about, delta of n minus 1. And so how does the circular convolution of this thing with that thing work? Well, first what we do is we make this x2 guy flip over. So this is x2 of minus m, but we flip it over in what sense? We flip it over in a circular way. So if I were to plot x2 of minus m, really it would be this, but then this, well, x2 of minus m, strictly speaking, would be the tall value here, and then a shorter one here, a shorter one here, and a shorter one here. But that's already outside the extent of the thing. So what you do is you make it periodic, and you take one period of it, and that's what it happens. Maybe I should draw on a piece of paper to explain that more clearly. I will in a second, but let me finish this here. So this is x2 of minus m. And what's x2 of 1 minus m in a periodic way? This thing gets shifted over by 1 that way. So this sample from here comes over here, and that's how the thing looks like. So at x2 of minus m, what I do is I multiply this sample by this sample. Let me point with a better pointer. Yeah, this is good. So to compute the output, yeah, the output is also here. So to compute the output at this point, okay, I start with x2 of m. I do x2 of minus m, but in a circular way. I get this. Then I multiply this point by that point, this point by this point, this point by that point, this point by that point, and that point by that point. And what number do I get? Well, I only get, everything is 0 except the product of this guy by that guy. So I get that little bump here, right? And then I do x2 of 1 minus m. That's a shift. So that would make this sample go from here to here, and then drag it by 1. Remember, it's all in a cylinder. It's a circular way, right? So when you do that, now I multiply this sequence by that guy. So it's this value times 0, this value times that, this value times this, and this value times that, and this value times that. So the only non-zero one is this times that. So I get a tall guy, the same height as this. I'm assuming this is just 1. So I get the same height as I have here. And I keep doing that. So I do one more circular shift, and this time this guy spills over here, and I drag the whole thing to the right by 1. And then do pointwise multiplication with this guy, and I get this. Okay? Is this clear to most of you? Or all of you? Yeah? Okay, good. So that's how really circular convolution, that's sort of an example of a circular convolution of two sequences. I start with an endpoint, I make this new one endpoint, and I get an endpoint answer. And so, whereas with linear convolution, if you linearly convolve the delta function that was delta of n minus 1 with this sequence, it'll just shift the whole thing to the right. right? That would be linear convolution, but this was circular convolution. It shifted the whole thing to the right, but because it spilled over n, that thing wrapped around and came back here. Okay? So I'm going to make a note here, figure 8.14 of Oppenheim and Schaefer here. And so what is the circular convolution of these two sequences? So can you zoom out, please? Great. So x3 of n, which is this x1 of n circularly convolved with x2 of n, is just summation it's just it's one period, just like we defined. It's r sub n of n, one period of x1 of n periodically convolved with x2 of n. Or in this example, what we saw, you don't have to make everything periodic. Another way of doing it is to say it's a summation from m equals to 0 n minus 1. You keep one of the sequences, x2 of m, non-periodic, and then the other one, you make it periodic and shift it, which would be x1 of n minus m, rn of m. Okay? So what's happening here, what I'm saying is we kept the delta function fixed, and the other function that consisted of 4 or 5 points, we dragged it around, but we dragged it in a circular way, and that's what this thing is saying, is you shift it by m, when m is 0, 1, 2, 3, etc. You make it periodic, and you just extract one period. And that is the same as, zoom in here, that is the same as this sequence. So we kept the x1, the delta function, the same, right? And x2 is the thing that we periodically shifted. This was shifted, in here it's shifted by 0, and here it's shifted by 1. And when you shift it by 2, this comes over here, and then dragged everything to the 1, by 1 to the right. And then this comes over, drag everything to the 1. So strictly speaking, that picture that I showed you corresponds to this sort of an operation. So that's all fine and good. Let's talk about something a little bit more interesting. Let's talk about example number 2, circular convolution of two different sequences. Suppose that I have x1 of n is equal to x2 of n, and it's equal to 1 for this length, for L minus 1 to 0, and it's 0 otherwise. Okay? And I'm going to consider two cases. I'm going to talk about an n-point circular convolution of x1 and x2. And remember, the length of this is L, but I'm going to talk about n-point circular convolution. And I'm going to consider two different cases for n. Right? Could you zoom up? Yeah. So I can consider two cases of n. One is n equals L, and the other one is n equals 2L. Okay? So how would this thing work? Well, let's first consider the case where, case 1, where n is equal to L. Okay? So what would be the L-point circular convolution of these two L-point sequences? Look, x1 it goes from 0 to L minus 1, and x2 goes to 0 to L minus 1, and I'm going to do the first time I'm going to do an L-point circular convolution of these two things. That means I make both of them periodic with period L. I take their periodic convolution, and then I extract one period. In case 2, I'll pad them with a bunch of zeros. I'll pad this one with a bunch of zeros, and I make their length to be 2L minus 1 and 2L minus 1. So I pad with L extra zeros here and L extra zeros here. Then I make this thing periodic with period 2L. Then I make this thing periodic with period 2L. take the periodic convolution with period 2L, and then extract one period of that 2L point sequence. So you can see the difference between these two cases, right? In one case, all the periodicity is with period L. In the other case, all the periodicity is with period 2L. And how do I make a sequence with 2L points? I just pad it with enough zeros. Okay? So let's consider the easier case, where case n equals L. So we can use DFT to do our circular convolution. Circular convolution. And how do we do that? We take a n-point DFT of x1. You take a n-point DFT of x2. In this case, x1 and x2 are the same. You multiply the two things together and take inverse DFT, and we're all done. Okay? So case 1, you take, and why is it that I'm taking n-point DFT? Because, or L-point DFT is because that's how circular convolution works. Is to do circular convolution is the same as multiplying the two sequences, multiplying the DFT of the two sequences with that period. So you take n-point or L-point DFT of x1, and what do I get? I get x, and I'm going to put this little n here, or rather this little L here, showing that I'm taking an L-point DFT of x1. So L of k is the summation from n equals 0 to L minus 1, x1 of n, e to the minus j 2 pi nk over L. So then xL of k is nothing but L when k is equal to 0, and it's 0 otherwise. Okay? And this is the same for x1 and x2, because x1 and x2 are the same sequences. Remember, up here, they're identical to each other, so it just doesn't make any difference. And so I multiply xL of k by another xL of k. So x3 of k, which is their L-point circular convolution. So x3 of k is the L-point circular convolution of x1 and x2 of the DFT of those two guys, is given by xL of k times xL of k, the product of those two things, because that's how things work, and you get L squared for k equals 0 and 0 otherwise. And now I take an L-point DFT, inverse DFT of that, so an L-point inverse DFT of x3 of k, and what do I get? I get L for n between L minus 1 and 0, and I get 0 otherwise. Okay? So this is the this is sort of the straightforward case. Pictorially, this is shown here. Let's zoom in as soon as you can. So this is a L-point sequence x1. This is another L-point sequence x2. And I was going to take L-point circular convolution of them. That's the same as taking L-point DFT of this, L-point DFT of that, multiplying them, take L-point inverse DFT, and that's what you get. If this was of length L, this was of length L, this is going to be, the height of this is going to be length L as well. So does this sequence look at all like a linear convolution of these two things? No. It's just circular convolution. And why is it that it's a constant height? Because x1 is a constant height sequence, 1, 1, 1, 1. x2 is a constant height sequence, 1, 1, 1, 1. And no matter what position I am, it's 1 times 1, 1 times plus 1 times 1 plus 1 times 1 plus 1 times 1 plus 1 times 1. And I click one more angle, it's 1 times 1 plus 1 times 1, etc. Another 1 times 1, that's why you get a constant height. Not a surprise. Everything makes sense, right? Now let's do the next experiment, case 2, whereby, again, we have these sequences. Let me not lose sight of our sequence. And zoom up. So case 2, what we do is n is equal to 2L. In other words, I'm going to do a 2L point circular convolution of x1 and x2. And if x1 has only L non-zero values, how can I make the 2L point circular convolution of those things? As I just said earlier, I'll pad it up with a bunch more zeros. At index L, 0, L plus 1, 0, 0, 0, 0, 0, all the way to here. So I pad with L extra zeros, and I get a what? A 2L point sequence. And I do the same thing with x2. Remember, x1 and x2 are the same things. Then I do their circular convolution. Then it's no longer true that it's 1 times 1 always. I'm not going to get a constant anymore because there's a bunch of zeros here, right? And so how do I find out what the circular convolution of these two things is? The same thing. I'm going to make a periodic sequence out of this with period 2L, and then periodically convolve it with itself, and then take one period, and that's the answer. And notice that that's going to be different than if we did everything with period L. Here I padded it with 0, I made it 2L, and now I'm going to make everything periodic with period 2L. So compute the 2L point DFT of x1, and that's given by what? Summation from n equals 0 to 2L minus 1 of x1 of n times e to the minus j 2 pi nk over, now what? What should go here? 2L. And by the way, I don't have to go all the way to 2L minus 1. Here I can go all the way to L minus 1 because these are all zeros. So n equals 0, L minus 1, x1 of n, e to the minus j, 2 pi nk over 2L. This is different from an L point DFT of that sequence. Even though the index is going to L minus 1 only here, it's different because an L point DFT would have just L here. And what am I doing, by the way, here? If I'm sampling the DFT of a DTFT of x1 at twice as many points as before, right? I'm taking a 2L point DFT of an L point sequence. So in the Z plane, if you will, if I was going to get L point DFT, these are the samples. If I do 2L point DFT, I get those plus the ones in between. I get twice as many samples. That's what effectively this is doing, right? So if I was going to do a 2L point circular convolution of these guys, I take a 2L point DFT of sequence 1, 2L point DFT of sequence 2, which in this case is the same thing, and then multiply them together. And then take inverse DFT. Okay, so here's 9. So here it is. L numbers going in, 2L numbers coming out. That's the 2L point DFT of x1. And we call that, by the way, x sub 2L of k, just to distinguish it from x sub L of k. X sub L of k is we took L point. This is x2L of k. Now how do I compute the circular convolution? Well, the 2L point circular convolution is equal to inverse DFT, a 2L inverse DFT of a product of x2L of k times x2L of k. That's the 2L point DFT of x1. That's 2L point DFT of x2. Multiply them together, take 2L point inverse DFT, and out comes the answer. And that then gives me is equal to x1 circularly convolved with x2, but with 2L point, not L point this time. Okay? And how does that look like? What do I get in that case? Again, let me open up, to draw the picture, let's open up Oppenheim and Schaefer and look at figure X16. How does, intuitively speaking, how does the circular convolution of these two things look like each other? Zoom in, please. Great. So this is our x1 sequence. It has L non-zero values of 1, 1, 1, 1, 1, and it has L zero values of 0, 0, 0, 0, all the way to 2L. Oppenheim likes to call this N, but I think it's just because in this case n is 2L, just think of this n as 2L, okay? And this is our x2. It has L non-zero values, 1, 1, 1, 1, 1, and then L zero values, 0, 0, 0, 0, 0, etc. And how do we do circular convolution of these guys? The same way as we did the other example. Just keep x1 stationary and flip and drag x2, except that because we're doing circular convolution, it's flip and drag in a circular way, right? So how do I compute x2 of minus n? Well, this is x2 of n. To compute x2 of minus n, I keep 1 here, and all of these guys here get flipped over on this side, okay? And this is, and yeah, I think this is a good point for me to not draw it. It's too much hand waving. Let me attempt to draw it, because then I can explain it a lot better than just hand waving. So here's our x1. And what does it have? It's this, 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 and then 0, 0, 0, 0. This is 0. This is 3, 4, 5, 6, 7. These are the indices, right? And now what is x2 of n? x2 of n is the same thing. It's 1, 1, 1, 1, and then 0, 0, 0, 0. Now, x2 of minus n, and I'm going to draw this really small. If I were to draw x2 of minus n, it would be a 1 here, and 1 here, a 1 here, a 1 here, and then 0, 0, 0, 0. But that's x2 of minus n as if, you know, it's just flipped it. But because we're doing circular convolution, how does it do? Well, I have to make this guy periodic. So let's, x2 of minus n periodic is what? This thing duplicated here, duplicated here, duplicated here, etc. So let's duplicate it. And then take one period of it, and then once we take one period, we multiply pointwise by x1. So how would it work? Well, let's periodically repeat this guy right here. So it'll be 0. This guy would come here as 0. This guy would come here as 0. This guy would come here as 0. And this guy would come here at 1. This guy would come here at 1. This guy would come here at 1. And that's it. This guy, we only needed one period. We only want to go from 0 to 7 indices. This guy is already in the range between 0 and 7. I can repeat it here, but I only want to take one period of this x2 guy. And now I multiply this period that's in the correct range of indices, which means these set of numbers, I'm going to pointwise multiply them by these set of numbers. And so what's going to happen is I'm going to multiply 1 by 1, and then 1, these are all 1 times 0, 1 times 0, 1 times 0, 0 times 0, 1 times 0, 1 times 0, 1 times 0. So the only contribution is from this guy, right? It's 1 times 1. So add the answer at the index n equals 0, the answer is just 1. Why? Because I did my pointwise multiplication. What's the answer at index n equals 1? Well, to do that, I have to pretend this is like a train, and you just have a string attached to this end, and you just click it one index to the right, like that, okay? And how would that look? Well, let's just plot it. So this guy will move here. We'll have a 1 here, a 1 here, okay? And the rest, so this one would move here, this guy 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 would move here, and this guy would move here. And remember, I only need 7 of them. 0, 1, 2, 3, 4, 5, 6, 7, right? So now so this is for position 1. That means the answer for index n equals 1. What's the answer there? Let's do our pointwise multiplication by x1. It's this times that, and then 0 times this, 0 times that, 0 times this, 0 times that, 1 times 0, and 1 times 0. So the only two contributions from 1 times 1 plus 1 times 1. So the answer will be 2. Is that clear to people? And the same thing keeps going on. So this was x2 of 1 minus n periodicized, but multiplied by r and n. In this case, in the top case, I kept showing all the periods. Here, I'm just looking. So think of it like that. I'm going to get a string, and I'm going to pull this thing now by 2 indices. Click, click, and then take 1 period of it, and then I keep doing that. Now, if I do all of that, this is what I get. As I pull more of them in, it starts with being 1, and then 2, and then 3, and then 4. It peaks up and it comes down like that. Okay? So that is the 2L point circular convolution of those two constant height sequences. And what can you say about that? Right. The linear convolution of two constant sequences of height 1. Oh, looks like that's why you couldn't see it. Sorry. Can you zoom out? No wonder. So the person who said it, how did you know the answer if you didn't see it? It's in the homework. Right. It was in the homework you did today, right? Wow, God, I'm just repeating the homework. Right, right. So the two things just result in a linear. Actually, the homework didn't exactly explain why this works. It asked you to do it, right? And you saw that it's true. So I'm talking about trivialities right now. But now what I'm going to talk about is why is it that this happens? Can we formally prove that this thing is going to? Well, informally, you can already see what's happening. Intuitively, why is this happening? It's the zeros that we added prevented these things to interfere with each other, right? When I shifted by 1, it's this sort of multiplication. When I shifted by, I don't know, something else, it's this sort of multiplication. It doesn't, the zeros sort of enables the destructive interference of the rotated stuff with each other, okay? So let's now move on and actually prove. So our goal here is just prove that indeed padding with enough zeros. Can you fix the camera, please? Great, thank you. Can convert circular convolution to linear convolution. And what do I mean by that? Well, I mean, suppose I have x1 of n, which is an L-point sequence, and suppose I have another sequence, x2 of n, that's a p-point sequence. And suppose I have another number, n, that's larger than n, and n that's larger than p as well. N is larger than both L and p. And my goal, ultimate goal, is to compute the linear convolution. x3 of n is x1 convolved with x2, which is just the linear convolution. So goal is to find linear convolution. And I just want to use DFT to do that. That's my goal. So what's the expression for x3 of n? Well, it's summation x1 of m, x2 of n minus m. That's the definition for linear convolution. And we can easily show how all of these things work by falling back on some basic principles. And what is that basic principle? It's just going through the DTFT route, right? So you have this thing DFT. Sometimes we go through the DFS route to show its properties. Sometimes we go through the DTFT route to show some of its properties. So what can we say about the DTFT of x3 of n? Well, it's x3 of omega, where it's defined by summation over n, x3 of n, e to the minus j omega n. And x3 of omega is just x1 of omega times x2 of omega. Okay? Where that we already know because convolution holds true. For linear convolution, straightforward multiplication of DTFTs does the job. So this is DTFT of x1, and this is DTFT of x2. Okay? Now what I'm going to do is I'm going to sample this x3 of omega at n equally spaced points. And remember, I'm sampling it at n, not at L and not at P. L and P are those are the length of these sequences. Like L could be 5 and P could be 5. or L could be 10, P could be 5, but N is larger than both of them. And I still haven't told you what N is. I'm not telling you how many equally, how is N related to L and P. And I'll keep it general until the last minute, where when we consider different values of N. And the upshot of this whole discussion is that if you pick N large enough, then DFT will do the job. And the goal of this derivation is to tell you what large enough means. Okay? So let's keep N as a general number. So here's I have x3 of omega, and I'm going to sample. This is another one of those thought experiments. I'm going to sample x3 of omega at n equally spaced points. And I'm going to call that y of k. And then, so y of k, in some sense, is just x3 of omega, evaluated at omega equals 2 pi k over n. And then I'm going to take inverse DFT of y of k, and what happens then? And I'm going to take n-point inverse DFT of that, so I get another n-point sequence. And can anybody say what we get here? Remember the thought experiment in last time's lecture. If you start with an arbitrary DTFT, you sample it at n points, and take inverse DFT of those n points, how is that n-point sequence related to the original sequence? How is it? Is that original sequence replicated with period n and take one period, right? That was the thought experiment from last time. So it is the original sequence x3 replicated n plus rn summed over r, and just one period of it. So it's that for n between 0 and that, and smaller than n, and it's 0 otherwise. That was the thought experiment last time. Okay? Okay. So another thing that we know, separate from this thing, let's keep this in mind. Let's just switch gears just a little bit. Another thing that we know from just general DTFT properties is that, well, y of k is equally spaced samples of x3 of omega, but x3 of omega we already know is x1 of omega times x2 of omega. So put those two things together, y of k is then x1 of omega sampled at equally spaced points, 2 pi k over n, times x2 of omega sampled at 2 equally spaced points at n. This is just straightforward from property of convolution and DTFTs, and the fact that the way we constructed y of k. So what is x1 of omega evaluated at n points? It's a n point. So so come back here. We have a L point sequence. We took its DTFT, got x1 of omega, and we're sampling that DTFT at n points. What do we get? And n is larger than L. What do we get? And take inverse DFT of that n-point sequence. What's the answer? You have a 10-point sequence. It has a DTFT x1 of omega. You go to x1 of omega and sample it at 15 points. And then you take 15-point inverse DFT of that. You get a new sequence. How is that new sequence related to x1? It's x1 with 5 extra zeros. So what I'm trying to say here is that this thing is the n-point DFT of x of n. So that's nothing but n-point DFT of x1. And this thing is nothing but n-point DFT of x2. Okay? So what can we say about inverse DFT, n-point inverse DFT of y of k based on this thing? Well, it's the circular convolution of x1 with x2. Right? Because this is n-point, I'm multiplying n-point DFT of some sequence with another n-point DFT, and I get y of k. So multiplying endpoint DFTs corresponds to endpoint circular convolution. That's the property that we just proved today. That's the way today's lecture started. So I'm going to use this box together with this box. Let me show them. Can we show both of? Yeah. So I'm going to combine these two things together now. So inverse DFT of y of k on one hand is this, and on the other hand, it's this. So combining these two things, what do I get? I get that endpoint circular convolution of these two guys is equal to summation from r minus infinity to plus infinity x3 of n plus rn for n in between n and 0, and it's 0 otherwise. Just the left-hand side is the same. I'm just equating the right-hand sides. Okay? So that's what I was after. This is the final thing I was after. And now that we've derived it, let's interpret to see what that means. What is the meaning of this thing? What is x3? x3 was just the answer for linear convolution, right? And these guys, so what I'm saying is that the circular convolution of these two guys is x3 periodicized with period n, and then taken one period out of it. It's the same linear convolution as we want, but make that periodic with period n and take one period of it. So staring at this, what can we do so that the endpoint circular convolution is exactly linear convolution? So let me write this down a little bit more. What this is saying is that in words, let's just turn it into English, endpoint circular convolution of x1 and x2 is the same as their linear convolution x3 periodicized with period n, and then take one period. So the steps are this. I convolve x1 and x2, I get x3. Then I make it periodic with period n, then I extract one period. And that is the same as endpoint circular convolution. So if I wanted the circular convolution to be exactly equal to linear convolution, what property should n satisfy? Well, we have to make sure there's no aliasing happening here, right? I am making x3 periodic with period n. And how can I make sure that x3 is not aliasized? What is the length of x3? What's the extent of x3? x3 is the linear convolution of x1 and x2, and x1 has L points and x2 has P points. What's the extent of L3? Everybody? That's right. So the extent of x3 has duration L plus P minus 1. So if I'm making it periodic with period n, I better make sure n is larger or equal to L plus P minus 1 to ensure there is no aliasing. And in that case, if I do all of these things, then hallelujah, one period of this is the same as endpoint circular convolution. And why is that so exciting? Is because we already know that DFT does circular convolution for us. In fact, how do I do the circular convolution of these two? Take endpoint DFT of this, take endpoint DFT of that, multiply, take inverse DFT. And if my n satisfies this, then I can use DFT to do linear convolution. Okay? So if I do this, then there's no aliasing. What that means is that means x3, i.e. linear convolution, can be computed using just circular convolution. But proper point circular convolution. This is an endpoint circular convolution. Okay? And why is that exciting? Why am I excited that linear convolution can be computed just using circular convolution? But we also know that DFT can do circular convolution. So putting these two things together, you can conclude that DFT can do linear convolution. So what I did is I first related circular and linear convolution. I came up with a condition out here showing you what has to hold true for circular convolution to be related to linear convolution. And where's my last sheet here? Page 14. Oh, here. So here I related circular convolution to linear convolution. And then I came down here and said, look, how can I make sure that if I did circular convolution, I really nailed and I got my linear convolution? And the answer was, we better make sure this doesn't have aliasing. So we better make sure n is larger than L plus P minus 1. So that's it. Under this condition, circular and linear convolution are the same. Then I came down here and said, look, I can do DFT to do circular convolution, and I know now circular is related to linear convolution. Therefore, I can do DFT to do linear convolution, which is what I wanted to do. And the condition for doing that is n has to be larger than equal to L plus P minus 1. If that holds true, then the circular convolution of x1 and n2, n-point circular convolution, is exactly equal to x3 of n. No buts, no ifs, not a fact, which is exactly linear convolution. Why? Because of this. Because of that. If n is larger than p plus 1, this thing just reduces to just x3 of n, period. So what the whole thing is saying is that n-point circular convolution is of x1 and x2 is the same as linear convolution, as long as we do what? As long as n is larger than the duration or the extent of the linear convolution is larger than the extent of linear convolution. Okay? So pictorially, hold on a second. So pictorially, what's happening is this. Here's our x3, and let's say it has 0 to L plus P minus 1 non-zero points. Okay? So what I'm saying up there is that the summation x3 of n plus Rn is going to look like, if n is larger than L plus P minus 1, larger or equal, it's going to look like this, and then this, and then this, etc. For n larger than equal L plus P minus 1. But that same summation, x3 of n plus Rn, if n is smaller than L plus P minus 1, it's going to look like this. And then I'm going to get these problems. And that's why when I had two equal height sequences of 1, 1, 1, 1, 1, circularly come on with 1, 1, 1, 1. When I didn't pad it, these things were massively overlapping with each other, causing all sorts of problems. So what is this whole thing telling us? What is the recipe then to compute x3 of n, to compute the linear convolution? What are the steps that one has to take? Well, what we have to do, we have to prepare things in the right way to accomplish this circular convolution. This is an n-point circular convolution. So remember, x1 had only L points, right? Start from the beginning of our discussion, L1 had L points, L non-zero points, the region of extent of, and x2 had P points. So what are the steps that one has to take in order to do all of these things? First, step 1, pad x1 with n minus L points to get an n-point sequence. Pad x2 with n minus p points to get another n-point sequence. Points, I mean zeros, sorry. And now that I have the n-point sequences, I want to do circular convolution of these two things. But I've decided I want to do DFTs to do that. So step 3, take n-point DFT of the new sequences we got in step 1 and 2. And then step 3, take inverse DFT endpoint inverse DFT of the sequence in step 3, and that is linear convolution as long as n is larger than p plus l minus 1. So these are the steps you go through. You have an L point sequence. So let's say L is 10 and P is 5. So you pad x1. Actually, this is n minus L minus 1, right? Pardon? Oh, sorry. This is, that's true. So you start with, you have a 10-point sequence, and suppose you pick n to be 20. This is 10, L is 10, P is 5, and n is 20. So is n bigger than that 10 plus 5 minus 1? Yeah, 20 is bigger than 10 plus 5 minus 1. So we're all safe. So example is L is 10, P is 5, and n is equal to 20. So I pad x1 with 10 zeros. I pad x2 with 15 zeros, and I got two 20-point sequences. I take a 20-point DFT of the first one, 20-point DFT of the other one, multiply those 20-point DFTs, get a new DFT, take an inverse DFT of that thing, and I get a 20-point sequence. And as long as, and because this equation was satisfied, the new point sequence is the linear convolution of the two things, maybe padded with some extra zeros. Depending upon how much bigger is n than p plus l minus 1, that's how many extra zeros I get at the other end. Okay? I'm going to pause here. There was a question.
I have a question regarding the real hardware implementation of the linear convolution. Is there any point to use DFT to calculate linear convolution?
If you're doing large sequences, yes. What I haven't talked about, and that's perhaps 2 lectures down the road from now, is there's fast algorithms to do DFT.
I know there's FFT, you can calculate fast.
Right.
But
So depending upon what hardware you're talking about, certainly on a computer, if you're doing convolutions of very large sequences with each other, it makes sense to go through this route. But if you're doing small convolutions, it doesn't make sense to do that. So are there any questions about these whole concepts? So what we did, sort of in a nutshell, is related circular and linear convolution. And we already knew DFT does circular convolution, so now we can do DFT to do, and inverse DFTs to do linear convolutions. And essentially, one more time, when you do this padding over the zeros of these two sequences, what's happening is you're sampling their DTFT finer, in a finer way in the DTFT domain than you would have done otherwise. Okay? All right, I'm going to stop the lecture now. I'll see you all on Wednesday. And don't forget to pick up the solutions. Dan, you have the graded homework? Put it out there real quick.